Have you ever wondered why you burn your fingers when you touch a pen with a metal handle? No? The reason is that the heat is conducted from the bottom of the pen all the way to the handle. That's why you take one with a wooden or plastic handle. If you fill a cup with hot tea and you put a spoon in it, the spoon will heat up as a result of heat conduction. Today we will look at the conduction of heat in different materials. One of the first scientists who investigated heat conduction was Joseph Fourier, who lived from 1768 until 1830. He discovered that steady-state heat conduction in any material could be described by the following relationship. This equation shows that if the temperature difference between the liquid and the end of the spoon become larger, the heat flow increases. Also, the geometry of the spoon plays a role in the speed of the heat conduction, in particular the cross-sectional area of the spoon, A, and the length L. Lambda represents the heat conductivity of the material. For example, you know that you will burn your fingers faster if the spoon is made of metal than when the spoon is made of plastic. The reason is that a metal has a higher conductivity than plastics. Let's illustrate the difference in heat conductivity in different materials. For air, the conductivity is 0.02 watts per meter per Kelvin. For water it is 0.6 and for iron it is about 80. If you take copper, which is one of the best heat conductors, it's even 400 watts per meter per Kelvin. Well, we could pose the question, what can we do with Fourier's law? Let's illustrate this by means of the steady-state conduction through the spoon. This means that the temperature at the beginning and at the end of the spoon is constant, and that the temperature profile in the spoon is not time dependent. For simplicity, the spoon is represented by a bar. The bar has a cross-sectional area A and a length L. Now we could ask ourselves, what is the temperature profile of the entire bar? Heat conduction will only occur if there is a temperature difference between the beginning and the end of the bar. We assume that no heat is exchanged with the surroundings. As a result, the heat flow in the bar is constant. Further, we know that the heat conductivity and the cross-sectional area of the bar do not change over its length. If we now want to describe the one-dimensional heat conduction from x is 0 till x is L, we start with Fourier's law. In this example, the heat flow, the heat conductivity and the cross-sectional area of the bar are constant. As a result, the temperature gradient is also constant. This leads to the following equation. If we rewrite this equation in a temperature and place dependent part, we get the following result. Integration between t is t0, which is the beginning of the bar, till t is tx, which is a certain position x along the length of the bar, gives us the temperature profile in the bar. This shows that we obtain a linear temperature distribution for steady-state heat conduction in the bar. If we now know the temperature difference between the beginning and the end of the bar, we can calculate the heat flow. The heat flow phi q can now be calculated using the following equation. In conclusion, we can say that we can derive the one-dimensional temperature profile in simple geometries, like a bar, by applying Fourier's law for steady-state heat conduction. With this information, you should be able to make the exercises of this week. If you want to see more about Fourier's law, well, take a look at the spark. Well, thank you for your attention.